Welcome to the video presentation about our paper titled Experimental Identification of Dynamic Piezoresistivity of Fused Filament Fabricated Structures. The paper was published in Additive Manufacturing Journal. Fused filament fabrication, shortly FFF, also known as fused deposition modeling or sometimes just 3D printing, is one of the additive manufacturing technologies. In FFF, thermoplastic material is heated in the extruder and then deposited layer by layer on the build plate. In the past, filaments used with FFF were only suitable for structural purposes. Currently, there already exist commercially accessible filaments that exhibit sensing and actuating properties, such as piezoresistivity, piezoelectricity, capacitance, and ferromagnetism. In our paper, we are focused on the piezoresistivity. In order to exhibit piezoresistivity, FFF structure has to be electrically conductive. Thermoplastic materials are, however, insulators. Conductivity is achieved by dispersion of conductive particles in non-conductive matrix. When stress or strain is applied to electrically conductive FFF structure, conductive paths formed by conductive particles rearranges and electrical resistance changes. This resistance change is called piezoresistance, while change in electrical resistivity is called piezoresistivity. Piezoresistivity is highly influenced by FFF process parameters. There is currently no standard experimental procedure for the evaluation of piezoresistivity under static or dynamic mechanical load. Therefore, an experimental method for the evaluation of piezoresistivity of FFF structures under dynamic mechanical load was developed. The assumptions of the Presposed method are: material is deposited in single direction, approximately 100% infill is used so that structure can be treated as a homogeneous continuum, structure behaves linearly, and orthotropy can be assumed. To better understand the proposed method, some theoretical backgrounds have to be discussed first. Let's assume an isotropic resistor with resistance R. Resistance depends on length, cross-section, and electrical resistivity of a resistor. When stress is axially applied to the resistor, resistance changes. Resistance changes due to the change in resistivity and change in geometry. Change in geometry represents change in resistor's cross-section and length. In structures with strong piezoresistive effect, change in resistivity is dominant and is therefore more interesting for the observation. Material model of piezoresistivity is similar to Hooke's law and is for autotropic material expressed in matrix form. Here, quotient between resistivity change due to stress and initial resistivity when no stress is applied is related to the mechanical stress through the matrix of piezoresistive coefficients. For an orthotropic material, there are 12 distinguishable piezoresistive coefficients. In the proposed method, we are interested on a special case where resistivity and stress in the same direction are observed, particularly when stress and resistivity are observed in the material deposition direction, when they are observed perpendicular to material deposition in horizontal plane, and perpendicular to material deposition direction in vertical plane. Piezoresistive coefficient can be determined by applying stress to the FFF structure in one of the principal directions and observing resistivity and stress. To observe three distinguishable piezoresistive coefficients, three perpendicularly oriented specimen types were proposed. Specimen was then clamped to the electrodynamic shaker, and copper wires were used to transform electric current to the specimen and to connect the specimen to external circuit used to measure electric resistivity. Additionally, force and acceleration were measured. To obtain reliable results, good electrical contacts have to be achieved. At first, surface was painted with a highly conductive silver paint, and afterwards, copper wires were soldered to the conductive copper tape, which was then taped to the painted surface. In order to determine piezoresistive coefficient, specimen was sinusoidally mechanically excited and force, acceleration and resistivity time signals were measured. Measured time signals were then using Fourier transformed to frequency domain. From static component of the resistivity amplitude spectrum, initial resistivity was determined, and from component at mechanical excitation frequency, resistivity change was determined. From acceleration and force amplitude spectrum at mechanical excitation frequency, stress in the specimen was estimated. As a result, piezoresistive coefficient at a certain mechanical excitation frequency was obtained. To evaluate the applicability of the proposed method, piezoresistive coefficients in 55 to 220 Hz mechanical excitation frequency range were measured. The lowest piezoresistive coefficient was obtained in the material deposition direction, followed by direction transverse to material deposition direction in horizontal plane and in vertical plane. Obtained piezoresistive coefficients showed no frequency dependence, which is a good information for development of dynamic sensors. The developed method represents first systematic approach to the observation of piezoresistivity of FFF structures where effects of material deposition direction are isolated. Experiment is designed in a way that boundary effects of clamping and electrical contacts can be neglected. Additionally, frequency dependence of a piezoresistive coefficients can be investigated. The developed procedure can be extended to the determination of remaining coefficients by applying electrodes perpendicular to mechanical excitation direction. However, the influence of boundary effects on the identification of piezoresistive coefficients should be investigated in some more detail. Through the evaluation of applicability of the method, it was observed that piezoresistive coefficients do not exhibit any frequency dependence in examined frequency region, and that higher piezoresistive coefficients are observed in the direction perpendicular to material deposition direction. Obtained coefficients can be used in numerical and analytical models to predict the behavior of piezoresistive sensors. In the future, proposed experimental method can be used to investigate the influence of FFF process parameters on the dynamic piezoresistivity. If you enjoyed the video presentation and would like to get some more information about the proposed method, we invite you to read the published paper.